We now conclude this lecture on RNN with a discussion on backpropagation and several regularization techniques. To keep things simple, we are not considering LSTM and GRU, but classic RNN instead. To train this network, you need to compute the gradient using a backpropagation equation and then use it inside a gradient descent procedure. Let us consider this stylized version instead. You are first going to initialize the weights of the network. We have seen different initialization techniques in the previous section. Then, in a classic network, you would need to compute the gradient of the overall loss, which would require you to pass through the network a large number of times. Indeed, considering the loss associated to the last prediction requires to pass through the whole network, since the last prediction depends notably on the first hidden states. Such a procedure would be too time-consuming and may even be infeasible in practice. We use instead the truncated backpropagation, which works as follows. You still initialize the weights of the network as before. Then you choose a small number of steps, let's say 7. You are going to use the first 7 inputs, do a forward pass in the network, this corresponds to the gray arrow, to obtain predictions and the corresponding losses. Then the losses are averaged and you can backpropagate the gradient through this small portion of the network, the red arrow. Since this network part is small, it is possible to compute the gradient and to use it to update the weights in the network. Recall that the weights are shared through the network, so updating the weights at the beginning also updates the weights everywhere in the network. This is the first step. Now you can use the weights and the first 7 observations to compute the sequence of hidden states, first gray arrow. You are then going to compute the next hidden states using the next 7 inputs, here 6 in the picture corresponding to the second gray arrow. With these 6 additional inputs, you can build 6 predictions and compute the corresponding loss. You can then average the loss only along these 6 predictions. Then you are going to backpropagate the gradient of this loss, but only along the last 6 steps of the network, the red arrow. This will give you a gradient that you can use to update the weights. You can then repeat the process. This is called truncated backpropagation because you split the sequence into smaller pieces and you backpropagate the gradient only along these small portions. Note that by doing so, you increase the forgetting phenomenon of RNN, since the network is unable to remember that the first hidden state has an influence on the last predictions. You should then find a good trade-off for the number of steps used in truncated backpropagation. A small number is computationally efficient, but increases the forgetting phenomenon. Finally, you can also add regularization to improve the generalization capacity of RNN. As for classical neural networks, you can use L1 or L2 penalization. You can also enforce the network stability by considering a loss which computes the difference in L2 norm between a hidden state and the previous one. This enforces the norm of the hidden states to be similar, therefore preventing vanishing or exploding hidden states. Experiments on language modeling and phoneme recognition show state-of-the-art performances for this approach. Dropout can also be used. You can also force the network to remember some random hidden states by using Bernoulli masks. You can look at the last reference to know more about that. This concludes this lecture on RNN. We have seen the major architecture of RNN with possible weight initialization, gradient derivations, some spatial units as GRU and LSTM, and the truncated backpropagation method widely used in RNN. You can find in the slides some applications of RNN to text data mostly. Don't hesitate to take a look at these. See you in the next lecture.